seen just before the overload checking rule. So now we will see another rule, that is the detectable precedence rule. So the previous rule was just a rule that was able to detect that a failure situation was happening. The detectable precedence is doing something more. It's able to do some pruning of the domains of the activities. So let's see what this rule is doing together, and let's study first the intuition. I consider the activity B and C. Okay, what you can already see is that it's impossible to schedule C before B in this situation. B could come before C. For instance, you would place it here and C at the end. That would work fine. But it's impossible to place C such that it completes before the ending time of B. Okay, so we will say that C cannot be before B. Okay, and so as a consequence, C should come after B. Okay, that's one thing that we should remember. Then I will consider C versus A. And for the same reason, I realize that it's impossible to schedule C before A. You could try to place A here, and C to the leftmost position. They will overlap, so it doesn't work. And so you also can detect that C should come after A. So if I realize that C should come after B and after A, I will denote this like this. I have that C should come after A and B, okay, after the two activities, okay. And since they should come after A and B, the earliest possible ending of A and B is starting A there, and then you would place B, and B has a duration of 5. That would be 1, 2, 3, 4, 5, and so B would finish here, okay. And so since C must come after A and B, we know that C cannot start before this time. And this is why we will prune the beginning of C at the earliest it will come here. And this is what the detectable precedence filtering is doing. Okay. Now, with respect to C, I will denote this set A and B as the detectable precedence set. And so, or I will simply DP prec set. So detectable precedence set of I is A and B, okay? And the formal definition of A and B is all the activities such that the earliest start time of I plus the processing time of I would exceed the latest completion time of J minus Pj. Okay, so this is what you get as earliest completion time if you put it completely to the left, and this is the latest start time if you put the activity J completely to the right. And if there is an overlap, clearly, then J should come before the activity I. Okay, and so the filtering, if you have a situation like this, is that the earliest start time of I should be at least the earliest completion time of all the activities that you have detected that should come before the activity I. Okay, and again, you realize that there is something that you know is earliest completion time of a set of activities. This is a value that is normally NP hard to compute, but we have seen that we could compute efficiently a lower bound of it using the theta tree data structure. And so we will reuse the theta tree data structure to compute this very efficiently and implement this filtering rule in n log n for all the activities. This is what we will see now. Okay. Small modification is detectable precedence set of I, and now I remove the fact that the activity J that I will include in it must be different from I, okay? And so detectable precedence of I is this set minus the activity I if it possibly belongs to it, okay? Then I'm looking for a nested relation between the sets, because this is how I will be able to take advantage of the incremental data structure of the theta tree. And it's quite nice because if you would store the activities according to this, so earliest start time plus processing time, which is the earliest completion time, you realize that the sets are again nested. So the detectable precedence set of activity 1 is included in the detectable precedence set of activity 2 if you have sorted activity 1 and 2 such that the earliest start time plus processing time of 1 is less than earliest start time plus processing time of 2, and so on. So these subsets are nested if you have sorted the activities according to this order. And this is exactly what we are looking for. Okay? So that's the intuition. So What is the detectable precedence set? So I will consider the activities one by one in that order, and I have ordered the activities according to the earliest completion time. Okay, so they are sorted according to these values. Okay, and the one that will be included in the detectable precedence sets are all the ones that have latest start time that come before this. So for the first activity, I have only A, okay? So A is part of the detectable precedence set of activity 1, and that's it. Then I consider the next one, which is this one, and the two additional ones that should be included in the detectable precedence set are B and C, okay? And you see that the set are nested because according to this order, I can only add new activities in the detectable precedence sets. The one that were there before will remain. So if you would move the line up to there, you will additionally add the activity D, but you will not remove the ones that have already been included, okay? And so you include that one, and so on and so on. And this is very nice because we now have an idea on how to implement this very efficiently, okay, using the theta tree. So I will sort the activities first according to this order, okay? Okay, this is this order, and I will also sort the activities according to this order, okay? So I will sort them in two different ways to have a very efficient implementation of the detectable precedence filtering algorithm, okay? And so in one part of the for loop here, I will consider this order, and then this is the second order. I will consider it in this order. So as long as I have something that is detected, a detectable precedence, I will add it to the theta tree, and initially the theta tree is empty. Okay, so here what I'm computing here is that the theta tree, as an invariant, the theta tree here will be the detectable precedence set. The detectable precedence set of the activity I. Okay, so it will contain the detectable precedence set of the activity I at this point. And then we just need to use the filtering rule, and so the earliest start time of the activity I is equal to the maximum between the current state of the domain and the earliest completion time of the theta tree. And this is very important when you will do the practical exercise. Don't forget to remove the activity I, because the activity I may be included inside the theta tree, and we don't want it to impact the filtering. Okay? It is because what we have is not detectable prec, but detectable prec prime. And so we should remove the activity I from this set. Okay? And then you collect the maximum of them, and then you do the real update of the domain. So that's it for detectable precedence. So now let's study the time complexity. Again, here I'm sorting 2 times, so this is n log n overall. I have a loop here that is executing n times, but here, during this loop, I will only add an activity once, and so overall I will insert n times log n, so it means n log n overall for all this loop. Okay, no more than n log n. So total filtering is executed in n log n for all the activities on your resource. So very efficient algorithm, exactly the same time complexity as what we had for the overload checker.